Hello everyone, I am Ehsan and today I am going to talk about regularized submodular maximization at scale. This is a joint work with Shervin, Minaee, Moran, Feldman and Amin Karbasi. In this talk I will first define the regularized submodular maximization problem, then I will present algorithms to efficiently maximize regularized submodular functions, and finally I will briefly explain the real-world applications that we can solve with our proposed algorithms. Finding a diverse set of items, also known as data summarization, is one of the central tasks in machine learning. In order to effectively select a diverse subset of items, we need to define a measure that captures the amount of representativeness that lies within a selected subset. Finding sets that maximizes this defined measure enhances the danger of overfitting to the data, as adding more elements can never decrease the utility. To address this issue, as it is often done in machine learning, we need to add a simple penalty or a regularizer term. For this reason, in this work, we consider the problem of maximizing a function f subject to a cardinality constraint k, where f is defined as a difference of two functions g and l. Here g models the utility of a set and l is the regularized term which it models cost or the penalty. In theory, there is little hope to solve the most general form of this problem, as we need to enumerate overall sets of size k. Submodularity is a common property among many applications, where it makes combinatorial problems more tractable. A function f is submodular if for any two sets a and b, where a is a subset of b, the utility of adding a new element to set A is at least equal to the utility of adding that element to set B. Monotonicity is another common assumption where it says the utility of a set is always increasing if we add more elements to that set. If f is non-negative monotone submodular, vanilla greedy yields to a 1 minus 1 over e approximation algorithm. Note that in our problem, function f could be negative and non-monotone. While there are a lot of interesting works for non-negative non-monotone submodular functions, for the general submodular function where it can be negative, there is not much that we can do. Indeed, testing whether there exists a set S such that f of s is larger than 0 is NP hard. For this reason, we need further assumption on the objective f. Now consider a refined version of our problem, where f is the difference of a monotone submodular function g and a modular function l. Here g models the utility of a set, and cost of a set is the additive sum of the cost of elements in that set. Previous works have studied this problem in the offline setting, but in many practical scenarios, the data arrives at a very fast pace, there is only time to read the data once, and also on massive data, the greedy policies takes a few days or weeks to complete. In this work, we answered the two following questions for regularized submodular functions. Is it possible to summarize a massive dataset on the fly? And can we parallelize the greedy approach? Our streaming algorithm gets an input parameter r and provides a solution with a guarantee as a function of that parameter. For a set S, let beta s denote the ratio between the utility of S and its linear cost. By knowing the value of beta opt, by the way, in the paper we explain how to guess it, we can find a value for r in which it makes our theorem yield the strongest guarantee. From the definition of beta opt, it can be observed that for larger values of beta opt, the effect of the modular cost function over the utility diminishes and f gets closer to a monotone and non-negative submodular function. At the same time, we see that for large values of beta opt, the approximation factor approaches 1/2. A recent work proved that the 1/2 approximation ratio is optimal when the objective function is non-negative and monotone. Given these evidences, we conjecture that the threshold streaming achieves the best possible guarantee in the streaming setting. Similarly, we provide a distributed algorithm for maximizing regularized submodular functions. This algorithm does not require to keep multiple copies of the data. Interestingly, it improves over the state-of-the-art algorithm for monotone submodular functions. In this paper, we also studied the applications of regularized submodular functions in mode finding for strongly like concave distributions and several video, location, and text summarization tasks.